Hello, friend. Welcome to Science for Sleep. Whether you have returned tonight or are discovering this channel for the first time, this is a quiet place to slow down, learn something gentle, and let the day gradually fade. Tonight, we are looking closely at green tea. A finished cup may appear simple. Pale green water, a little steam, and a few softened leaves resting near the bottom. Yet that cup carries the chemistry of a living plant, the choices of growers and tea makers, and a history stretching across more than 2,000 years. The first surprise is that green tea does not come from a special green tea species. Most true tea comes from one plant called Camellia sinensis. The same species can produce green tea, black tea, white tea, and oolong tea. Their differences are created mainly by the age of the leaves, the way they are handled after picking, and how far their chemistry is allowed to change. Chamomile, peppermint, and rooibos are prepared in a similar way, but botanically they are not tea. They are herbal infusions made from other plants. True tea begins with Camellia sinensis, an evergreen shrub with glossy leaves and small white flowers. If you enjoy these quiet journeys, you're welcome to subscribe. And if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find this calm corner of science, one sleepy listener at a time. Fresh tea leaves are still alive when they are picked. Their cells contain water, pigments, aromatic compounds, and active enzymes. An enzyme is a protein that helps a chemical reaction happen more easily. Once a leaf is bent, bruised, rolled, or cut, substances that were held in separate parts of its cells can begin mixing together. With oxygen present, enzymes help transform some of the leaf's natural chemicals. This process is called enzymatic oxidation. It gradually changes the color, aroma, taste, and chemical balance of the leaf. Black tea is allowed to move much farther through this transformation. Its leaves darken, and some of their original catechins are converted into larger compounds that help create the copper color and deeper flavor of black tea. Oolong tea is usually allowed to oxidize part way. White tea is handled gently and receives relatively little processing, although some natural oxidation still occurs as it withers and dries. Green tea takes a different path. Soon after harvest, the leaves are heated to reduce the activity of the oxidation enzymes. In much of Japan, this is done with steam. In many Chinese green teas, the leaves are heated in a pan or on another hot surface. The heat changes the shape of the enzymes, making it difficult for them to keep working. This helps preserve more of the leaf's green pigments and its original catechin pattern. Catechins are a family of plant compounds that contribute much of green tea's bitterness and dry, puckering feel. Green tea also contains caffeine and an amino acid called L-theanine. Amino acids are small molecules that living things use in many biological processes, including the building of proteins. L-theanine is especially associated with tea and has been studied for possible effects on attention, mood, and relaxation. Caffeine can block some of the brain's response to adenosine, a chemical signal that builds during waking hours and contributes to sleep pressure. These facts make green tea biologically interesting, but they do not turn every cup into medicine. A compound can behave one way in a laboratory dish, another way inside a digestive system, and still produce only a small or uncertain effect in a long human study. Dose matters as well. A brewed cup releases only part of the material contained in the leaf. A concentrated green tea extract may place the chemicals from several cups into a capsule or liquid dose. Those two forms should not be treated as though they have the same strength, benefits, or risks. The most useful view of green tea is therefore neither magical nor dismissive. It is a carefully processed plant drink containing measurable compounds, some with well-understood short-term effects and others with more complicated evidence. Before any of those compounds enter hot water or a human body, they are produced inside a slow-growing evergreen shrub. That shrub, shaped by soil, rain, sunlight, pruning, insects, and seasons, is where every cup truly begins. Camellia sinensis belongs to a plant family called Theaceae, the same family that includes many ornamental camellias grown for their flowers. It keeps its leaves throughout the year, which makes it an evergreen. In a tea field, the plants often appear as low, even rows that reach roughly waist height. That shape is created by years of pruning. Left to grow freely, a tea plant can become a large woody shrub or a small tree, with branches extending well above the reach of a picker. Growers repeatedly cut it back to keep the newest growth close to the ground. Over time, this creates a broad, level surface called the plucking table. The name describes the part of the plant where fresh shoots can be gathered again and again. A healthy plucking table contains young buds, soft new leaves, and older leaves beneath them. The youngest growth is removed for tea. The mature leaves are usually left behind because they continue carrying out photosynthesis. Photosynthesis is the process that allows a plant to use sunlight, water, and carbon dioxide to make the sugars it needs for growth. Those older leaves therefore help power the next flush of tender shoots. A flush is a fresh wave of growth that appears after a period of rest, rain, warmth, or pruning. Tea farming depends on this repeating cycle. New shoots emerge, selected leaves are harvested, and the remaining plant begins producing another layer of growth. The species itself contains a great deal of variation. One major cultivated form is Camellia sinensis variety sinensis. It usually has smaller leaves and has long been associated with China and with regions that experience cooler winters. Another major form is Camellia sinensis variety Assamica. It usually carries larger leaves and is strongly linked with Assam in northeastern India, where summers are warm, rainfall is heavy, and the growing season can be long. Modern tea gardens contain many mixtures of these inherited traits. Growers have selected numerous cultivars, which are named plant lines bred for useful qualities such as flavor, cold tolerance, yield, or resistance to disease. Hybrids also combine features from different tea populations. A small leaf plant can now grow far from China, while larger leaf tea can be found outside Assam. The plant surroundings continue shaping every harvest. Tea generally grows best in acidic soil. A soil pH between about 4.5 and 5.5 is often preferred. The pH scale measures how acidic or alkaline something is, with lower numbers showing stronger acidity. Tea roots also need dependable moisture, although standing water can deprive them of oxygen and encourage root disease. Well-drained soil allows rain to move downward while leaving enough moisture for the plant. This balance helps explain why tea is often grown on slopes and raised ground rather than in flat, waterlogged fields. Elevation can change the speed of growth. Cooler mountain conditions may slow the development of new shoots, while warmer lowland conditions can support faster production. Rainfall affects how quickly leaves expand. Cloud cover changes the amount of direct sunlight reaching them. Temperature influences enzyme activity, respiration, and the timing of each flush. Soil minerals, wind exposure, shade, and drainage also alter the raw leaf that arrives at the factory. Farmers work within these conditions by adjusting pruning, harvest timing, shade, and plant selection. The most valuable part of this managed shrub is often only a few centimeters long. At the tip of a branch sits a folded bud, followed by the first soft leaves. These tissues are growing quickly and contain more water than the tougher leaves below. Their cells are active, their surfaces are thin, and their chemistry is still changing. That makes them useful for delicate tea, while also leaving them exposed. Caterpillars can chew through them. Fungal spores can enter damaged tissue. Strong ultraviolet light can stress their cells, and a rough harvest can bruise them before processing begins. The compounds concentrated in these young shoots help the plant meet those pressures. Their bitterness, aroma, and stimulating effects reached human cups much later. Inside the living plant, they began as part of a chemical defense system shaped by insects, infection, sunlight, and injury. Within each tender shoot, thousands of chemical reactions are taking place at once. The leaf uses sunlight to build sugars, draws minerals through its roots, and produces specialized compounds that help it respond to the world around it. Tea leaves contain carbohydrates, proteins, minerals, green pigments, caffeine, amino acids, and hundreds of volatile organic compounds. Volatile compounds are small molecules that can easily enter the air, allowing them to reach the human nose as aroma. Some smell grassy or floral. Others produce hints of fruit, citrus, roasted nuts, or fresh wood after the leaf has been heated and dried. The tea plant also produces a large family of compounds called polyphenols. Polyphenols are molecules found throughout the plant kingdom, where they can influence color, growth, defense, and responses to stress. A major group of tea polyphenols is known as catechins. 4 important tea catechins are epicatechin, epigallocatechin, epicatechin gallate, and epigallocatechin gallate. Their shorter scientific names are EC, EGC, ECG, and EGCG. The latter receives the most attention in green tea advertising, although it is only one part of a much larger chemical mixture. Catechins contribute to the bitter taste of tea. They also help create astringency, the dry and slightly rough feeling that can remain in the mouth after a strong cup. Inside the living leaf, these compounds can affect insects, fungi, and bacteria that attempt to feed on or infect the plant. Controlled feeding experiments have found that several tea catechins can slow the growth of leaf-eating caterpillars. Their effects vary according to the insect species, the dose, and the mixture of chemicals present in the leaf. This variation matters because a plant compound rarely performs only one job. The same catechin may affect feeding, cell signaling, ultraviolet protection, or resistance to disease under different conditions. Caffeine also begins as part of the plant's own chemistry. It belongs to a class of substances called alkaloids, which are nitrogen-containing compounds that often have strong effects on animals. More precisely, caffeine is a methylxanthine alkaloid. Young tea buds and leaves commonly contain more caffeine than older, tougher leaves. Those young tissues are valuable because they are actively growing, making their protection especially important. Caffeine can discourage feeding in some insects and interfere with the growth of certain microorganisms. Its stimulating effect in humans developed from the way our nervous system responds to the molecule, many millions of years after plants began producing related chemicals. L-theanine has a different role. It is an amino acid made mainly in the tea plant's roots before being transported upward into the shoots. The plant uses nitrogen from the soil to help form it. Light conditions, season, leaf age, and cultivation methods can change how much remains in the harvested leaf. L-theanine later contributes to the mild sweetness and savory depth found in many green teas. Pigments also participate in the leaf's daily work. Chlorophyll absorbs light energy for photosynthesis and gives healthy tea leaves much of their green color. Carotenoids help manage excess light and can later break apart into smaller aroma compounds during processing. Flavonoids, which include catechins, can help absorb ultraviolet radiation near the leaf surface. The plant's chemistry shifts when damage occurs. A caterpillar chewing through a leaf breaks cells and releases chemical signals. Compounds related to the plant hormone jasmonic acid can then activate defensive genes in tissues beyond the damaged area. Production of bitter compounds may change. New volatile molecules can enter the air. Some of these airborne signals may affect nearby leaves or attract predators and parasites that attack the feeding insect. Fungal infection can trigger a different pattern of responses involving cell walls, defensive proteins, and antimicrobial compounds. Temperature, drought, intense sunlight, and nutrient shortages also alter the mixture. A leaf growing during a cool, cloudy spring may therefore contain a different balance of amino acids and catechins from one expanding during a hot, bright summer. Growers and tea makers inherit all of these biological changes when they collect the shoot. Heating, rolling, drying, and brewing rearrange the chemistry, but the raw material was built through the plant's responses to soil, weather, insects, and infection. The bitterness in a cup once influenced feeding. Its aroma began with molecules involved in growth and stress. The dry feeling left by catechins reflects compounds that helped a soft young leaf survive long enough to open. Human beings were gathering and preparing tea leaves thousands of years before caffeine had a scientific name, or EGCG could be measured in a laboratory. Traces preserved in ancient bowls and burial sites now provide the earliest physical clues to when this defensive chemistry entered human history. Long before anyone could measure caffeine or examine a tea leaf under a microscope, people explained tea's beginning through story. One of the best-known traditions centers on Shenong, a legendary Chinese figure connected with farming and medicinal plants. In the familiar version, leaves drift into water heated for him, changing its color and taste. The account remains an important part of tea culture, though it provides no verifiable date, location, or single moment of discovery. The physical history has to be rebuilt from much smaller traces. Tea leaves are difficult to preserve because they are thin, moist, and easily broken down by microbes, insects, and soil chemistry. After hundreds or thousands of years, a leaf may no longer look like a leaf at all. Its edges disappear, its pigments fade, and its tissues collapse into dark fragments. Archaeologists therefore examine several kinds of evidence together. A plant fragment can be viewed under a microscope for structures that survive after most soft tissue has decayed. Tea leaves contain calcium oxalate crystals, hard mineral formations produced inside plant cells. Their shapes and arrangements can help narrow the identity of an ancient sample. Researchers can also test residues for chemical markers. Caffeine is useful because it occurs naturally in tea and can sometimes remain detectable long after the leaf has lost its original form. Theanine, the amino acid strongly associated with tea, provides another clue when it appears beside matching plant structures. Several plants contain caffeine, and burial materials can become mixed or contaminated. Strong identification therefore combines microscopy, chemistry, dating, and the location where the material was found. One of the most important discoveries came from the Han Yangling Mausoleum near modern Xi'an in central China. This large burial complex was built for Emperor Jing of the Western Han Dynasty, who died in 141 BC. Among the burial goods were dried plant remains once placed as provisions for the emperor. The fragments no longer resembled the neat leaves found in a modern tea tin. Microscopic structures and chemical biomarkers identified them as tea. Dating placed the material at roughly 2,100 years old. Evidence suggests that softer buds or young leaf material had been separated from coarser parts. Their presence inside an imperial tomb shows that tea had enough value to be included among goods prepared for the afterlife. A second discovery carried the story far beyond the regions where tea plants grew. At the Gurgyam Cemetery in the Ngari region of western Tibet, archaeologists examined material from a burial dating to about 1,800 years ago. Ngari lies on the high Tibetan plateau, where cold winters, dry air, and elevations of several thousand meters make travel and farming difficult. Tea could not have been gathered from a nearby wild grove. It had been transported from lower and warmer growing regions. That journey took place centuries before the best-known medieval records of tea trade between China and Tibet. Even earlier evidence has emerged from a tomb associated with the ancient state of Zhu in what is now Shandong province. Inside a small porcelain bowl, researchers found charred plant remains dating to the early Warring States period, around 2,400 years ago. Microscopic features and chemical tests, including evidence of caffeine and theanine, supported their identification as tea. Fire damaged the material, while charring also preserved traces that might otherwise have vanished. The bowl does not reveal exactly how the tea was used. The leaves may have been boiled in water, eaten with other ingredients, prepared as medicine, or placed in the burial for ritual reasons. Early tea could take forms very different from the clear green infusion prepared today. These discoveries create separate points across time and geography, rather than a complete daily record. A bowl in Shandong, selected leaves near Xi'an, and tea carried onto the Tibetan plateau showed that human use had already become varied and far-reaching. For tea to spread beyond rare burial goods and regional customs, people needed dependable methods for growing it, processing it, judging it, and teaching others how to prepare it. Those methods would turn scattered leaves into an organized culture. By the beginning of the Tang dynasty in the year 618, tea had moved beyond scattered local use. Over the following 289 years, it became part of farming, taxation, trade, travel, and city life across much of China. Tea plants were cultivated in regions with suitable rain, soil, and temperatures. Finished tea could then be transported toward towns where the plant itself did not grow well. Government officials collected taxes connected with tea production and commerce. Merchants carried it along roads, rivers, and canals, linking mountain farms with large urban markets. The tea used during this period often looked very different from the loose, green leaves found in a modern packet. Fresh leaves could first be steamed to soften them and reduce unwanted changes. Workers then pounded or ground the leaves before pressing the material into molds. The finished cakes might be round, square, or shaped with decorative patterns. Compression made tea easier to stack, store, count, and carry over long distances. A solid cake also protected part of the leaf material from crumbling during travel. Preparing this tea required several steps. A piece could be broken from the cake and held near a fire until it became warm and lightly roasted. It was then crushed into smaller particles or ground into powder. The tea might be boiled in a metal vessel, rather than soaked briefly in a teapot. Salt was sometimes added, and older practices could include ingredients such as ginger, citrus peel, onion, or spices. Methods varied by place and period, so no single recipe represents every Tang household. The clear infusion made from whole loose leaves became more common much later. As tea drinking spread, people needed tools designed for each part of the process. Farmers required baskets and equipment for steaming and pressing leaves. Traveling tea had to be wrapped, tied, weighed, and protected from damp conditions. Inside the home, preparation could involve a brazier for heat, a kettle for water, a grinder, a scoop, and bowls made from fired clay. The quality of the fire mattered because smoke from poor fuel could affect the water and tea. The water itself changed the drink through its mineral content and freshness. During the 8th century, a writer named Lu Yu gathered this growing body of knowledge into a work now called the Classic of Tea. Lu Yu is believed to have lived from about 733 to 804. His book was compiled during the later part of the Tang dynasty and is often described as the earliest surviving major work devoted entirely to tea. It did not create tea drinking. Tea had already been cultivated and consumed for generations. The book organized existing knowledge into a form that readers in distant places could study and compare. Lu Yu discussed the appearance of suitable tea plants and the regions where they grew. He described harvesting, steaming, pounding, shaping, drying, and storing compressed tea. His attention also moved toward the equipment used for roasting and grinding, the quality of different waters, the management of fire, and the bowls used for serving. Even the timing of boiling water received careful attention. Water that had only begun to form small bubbles behaved differently from water boiling violently. Too little heat could extract the tea weakly, while long, forceful boiling could flatten its flavor and waste fuel. Written descriptions allowed these observations to travel farther than spoken instruction alone. A grower in one region could compare leaf quality with reports from another. A merchant could judge whether a tea cake had been properly dried or had absorbed too much moisture. Urban drinkers could develop shared expectations about color, aroma, preparation, and equipment. This created standards, even when individual preferences continued to differ. A bowl of Tang tea therefore depended on many people who might never meet. Growers cared for shrubs through changing seasons. Woodcutters and charcoal makers provided fuel for processing and cooking. Potters shaped bowls, while metal workers produced kettles, knives, and other tools. Boat crews and pack animals carried tea toward markets, inns, monasteries, and private homes. Roads, bridges, river ports, and warehouses quietly influenced whether the product arrived dry and usable. Tea had become a coordinated technology, built from agriculture, craft, transport, and written knowledge. Once those methods could be copied and carried, tea practice was ready to travel beyond the regions that had first developed it. The methods recorded in China could travel wherever ships, pilgrims, and written texts were able to reach. Tea entered Japan through several periods of contact rather than through one confirmed voyage. Some of the earliest connections appeared during the Nara period, which lasted from 710 to 794. Japan regularly sent official missions across the sea to Tang China. These journeys carried diplomats, scholars, craftspeople, and Buddhist monks between the two countries. Travelers returned with religious writings, medical knowledge, seeds, and unfamiliar customs. Tea was among the practices that moved through these routes. The earliest supplies were scarce and imported. Court officials and Buddhist communities had greater access than ordinary farming households. A Japanese record from the year 815 describes the monk Aichu serving tea to Emperor Saga. Aichu had spent decades studying Buddhism in China before returning to Japan. The emperor later encouraged tea cultivation in several provinces near the capital. These early plantings did not immediately create a nationwide tea habit. Imported goods remained expensive, while local cultivation was limited. Interest declined at times as official contact with Tang China weakened. Buddhist monasteries helped preserve parts of the practice through these quieter periods. Monks maintained libraries, gardens, kitchens, and regular schedules that could support tea preparation. Their travel networks also connected distant temples more reliably than many private households. The tea, they knew, would have looked unfamiliar beside modern Japanese sencha. Some arrived as compressed cakes made from steamed and pounded leaves. A portion could be held near heat, broken away, and crushed into particles. The material was then heated in water, sometimes with added seasonings. This preparation belonged to the same broad family of techniques described during the Tang dynasty. Modern sencha uses steamed leaves that are rolled and dried in narrow shapes. Modern matcha begins with shade-grown tencha ground into a fine powder. Neither method had yet developed when the earliest cake teas reached Japan. A major renewal came several centuries later through a monk named Aizai. He was born in 1141 and traveled twice to Song Dynasty China to study Zen Buddhism. After returning to Japan in 1191, he became closely associated with renewed tea cultivation and powdered tea practice. Japanese tradition says that seeds connected with Aizai were planted in areas including northern Kyushu and later near Kyoto. Tea gardens around temples offered protected places where selected plants could be maintained across generations. Aizai also wrote Kissa Yojoki, commonly translated as drinking tea for health. The work was completed early in the 13th century, around 1211. Its explanations followed the medical ideas available in medieval East Asia. Health was often understood through balances among organs, foods, seasons, and bodily qualities. Aizai praised tea within that framework and linked it with alertness, digestion, and disciplined religious life. Those claims came many centuries before caffeine, catechins, or the nervous system could be studied scientifically. Tea's practical place in monasteries was easier to observe. Powdered tea could help a tired monk remain attentive during long periods of study or meditation. Preparation also required measured movements and carefully maintained tools. Over time, tea moved beyond monastic settings. Warrior families and wealthy households adopted tea gatherings as forms of hospitality and social display. Imported Chinese bowls, jars, paintings, and utensils could signal education or status. Guests sometimes competed to identify teas from different growing areas. Later generations gradually placed greater value on restraint, local craftsmanship, and the careful arrangement of the tea room. The Japanese tea ceremony developed through this long process of change. Its mature forms grew during later centuries through the work of many tea practitioners, patrons, potters, builders, and Zen teachers. Architecture adapted to the practice through small rooms, low entrances, hearths, and garden paths. Local ceramics gained importance alongside imported wares. Agriculture also changed as growers selected plants suited to Japanese soils and climates. The tea that crossed from China, therefore, retained old methods, while entering a different network of farms, temples, and households. Compressed cake tea gave way to powdered preparations in important settings. Those preparations later existed beside new kinds of loose-leaf green tea. Farmers eventually learned to alter the leaf before harvest by controlling sunlight, then reshape it afterward with steam, rolling, and steady heat. By the early 18th century, powdered tea already held an important place in Japanese temples and formal gatherings. Many households, however, wanted a leaf tea that could be placed directly into hot water and produce a clear, fragrant drink. This required a different way of handling the fresh harvest. A major change came in the village of Ujitawara, south of Kyoto. There, a tea farmer named Nagatani Soen spent years experimenting with steamed leaves. In 1738, he developed the method now known as uji hand rolling. Fresh shoots were first exposed to steam. This early heating reduced the activity of the enzymes that drive oxidation. The softened leaves were then spread across a heated work surface covered with strong paper. Tea makers rolled them by hand while gentle heat removed moisture. Pressure moved water from the center of each leaf toward its surface, where it could evaporate. The process required repeated changes in motion as the leaves became drier. Broad movements handled the soft, wet material at first. More precise rolling gradually straightened and tightened the leaves. Near the end, careful pressure produced the thin, needle-like shape associated with high-quality sencha. The work could continue for several hours before the leaves were dry enough to store. Nagatani's method helped establish the foundation of modern sencha production. Sencha plants usually grow in open sunlight. Once the new shoots are harvested, the leaves are steamed, cooled, rolled, shaped, and dried. Modern factories use machines to reproduce movements once performed entirely by hand. Steam still reaches the leaf soon after harvest, and rolling still controls moisture, structure, and final shape. The dried needles unfold when they are placed in water. Broken cells release soluble compounds, while the remaining leaf tissue softens and expands. Tea makers also learned that the leaf could be changed before it was picked. In parts of the Uji region, growers began covering tea bushes as the spring shoots developed. Traditional coverings used frames topped with woven material or layers of straw. Modern farms may use dark synthetic screens stretched above the rows. For gyokuro, The plants are generally shaded for more than about 20 days before harvest. The covering blocks most direct sunlight. Reduced light changes how the growing shoot uses carbon and nitrogen. Leaves exposed to full sun convert more amino acids into other compounds, including some catechins. Shade slows part of that conversion, allowing more free amino acids to remain in the young tissue. L-theanine is especially important because it contributes sweetness and a rich, savory taste known as umami. Chlorophyll levels also rise as the plant tries to capture limited light. The harvested leaves therefore appear deep green and contain a different chemical balance from open-grown sencha. After picking, gyokuro is steamed and rolled into narrow leaves. Its preparation often uses cooler water and a high proportion of leaf, producing a concentrated infusion with sweetness, savoriness, and a gentle marine character. Another shaded tea follows a different path after steaming. This material is called tencha. Tencha leaves are dried without the repeated rolling used to make sencha or gyokuro. The flat, fragile pieces are later refined. Large stems and the thicker veins running through the leaves are removed. The remaining soft leaf material can then be ground between stone surfaces into a very fine powder. That powder is matcha. Matcha and gyokuro may begin with carefully shaded shoots, yet their final forms behave differently in water. Gyokuro is infused, and the leaves remain behind. Matcha is whisked into suspension, so tiny particles of the leaf are swallowed with the drink. A single species had now been directed into several distinct products through controlled light, steam, pressure, and drying. Sencha carried the marks of Nagatani's rolling method. Gyokuro reflected weeks of reduced sunlight followed by careful shaping. Matcha emerged from unrolled tencha refined and ground into powder. These familiar categories grew from deliberate agricultural experiments and generations of skilled labor. While Japanese growers were refining the leaf at this small and careful scale, merchants and governments were moving tea across oceans in quantities large enough to influence taxes, empires, and global trade. Fresh tea leaves contain so much water that most of their original weight disappears during processing. Roughly 4 to 5 kilograms of newly picked leaves may be needed to make 1 kilogram of finished tea, depending on the harvest and production method. The dried result is light, compact, and far less likely to spoil than a basket of tender shoots. A small chest could carry many servings across thousands of kilometers, while holding enough value to justify ships, warehouses, guards, and taxes. Dutch merchants began bringing Chinese tea into Europe during the early 17th century. Tea later gained a strong place in Britain. The English East India Company was purchasing it by the 1660s, including a documented order in 1664. Early British drinkers often encountered tea in wealthy homes, where imported leaves could be served with Chinese porcelain and other expensive goods. Government duties kept the legal price high, creating room for smugglers who landed untaxed tea along remote sections of the British coast. Spent leaves could be dried, coloured, and sold again. Willow, sloe, and other leaves were sometimes mixed into genuine tea to increase weight. The scale of illegal trade became so large that the British government changed its approach. The Commutation Act of 1784 sharply reduced the tea duty, helping legal imports compete with smuggled supplies. Tea had already become part of a much larger financial problem. British merchants purchased enormous quantities of tea, silk, and porcelain from China. Chinese sellers had limited interest in many British goods, so payment often moved eastward in silver. The East India Company tried to change that balance by expanding the sale of opium grown under British control in India. Opium entered China illegally, while silver began flowing back toward British traders. Chinese attempts to stop the trade helped lead to the First Opium War, fought from 1839 to 1842. A second conflict followed from 1856 to 1860. Tea, a drink associated with domestic comfort, had become tied to addiction, military force, and unequal treaties. British officials also wanted tea production outside Chinese control. In Assam, in northeastern India, they encountered tea plants related to the larger leaved variety, Assamica. Commercial plantations expanded during the 1830s, and the Assam Company was formed in 1839. Plantation systems brought roads, processing buildings, and export networks into growing regions. They also depended on harsh labor arrangements, including recruited workers who often faced low pay, disease, isolation, and strict control over movement. Tea cultivation later spread through other parts of India. In Ceylon, now Sri Lanka, coffee had dominated many highland estates until fungal coffee leaf rust devastated the crop. James Taylor established an early commercial tea plantation there in 1867. Within a few decades, large areas once planted with coffee had been converted to tea. These newer export industries often focused on black tea because its strong flavor, dark infusion, and durability suited British markets. Green tea remained deeply important in China and Japan, where long-established styles continued alongside changing machinery and trade. The global industry therefore altered where tea grew, who harvested it, and which forms reached distant consumers. Modern green tea now travels in far more shapes than the wooden chests of earlier centuries. Loose leaves may contain almost nothing beyond dried tea. Tea bags usually hold smaller particles that brew quickly. Bottled green tea may include sugar, acids, flavorings, or only modest amounts of brewed tea. A matcha dessert can contain flour, fat, and sweeteners, with the powder providing color and flavor. Capsules and liquid extracts may concentrate catechins and caffeine into doses far stronger than an ordinary cup. Cosmetics may use green tea ingredients on the skin without delivering them through digestion at all. A shared label therefore covers products with very different chemistry, calories, and biological effects. Global trade can move all of them, yet it still cannot create a fine tea from unsuitable raw material. Every shipment begins with the condition of a short-lived shoot, the weather that formed it, and the moment it was removed from the plant. At the tip of each tea branch, a pale bud begins to unfold above the older leaves. A common harvest standard is described as 1 bud and 2 leaves. The phrase refers to the soft terminal bud and the first 2 young leaves directly below it. It is a useful target for many fine teas, though it is never a universal rule. Some styles favor only a bud and 1 leaf. Others use larger shoots, mature leaves, or pieces gathered later in the growing season. The age of the leaf changes what the tea maker receives. Young shoots contain a high proportion of water and active cell material. They also tend to carry more free amino acids and caffeine than the tougher leaves farther down the stem. Catechin levels change with leaf position, sunlight, cultivar, and season. As a leaf expands, its cell walls gain more cellulose and other structural material. Cellulose is the strong plant fiber that helps the leaf hold its shape. Older leaves therefore become thicker, firmer, and more resistant to damage. Those changes affect flavor and processing. A tender shoot can be rolled into a fine shape with less force. A mature leaf contains more coarse fiber and may produce a stronger, rougher infusion when handled in the same way. Harvest timing adds another layer. Tea plants grow in waves called flushes. A flush begins when resting buds open and send out a new set of shoots. In Uji, near Kyoto, the first major harvest commonly begins in late April and continues through May. This spring crop is called Ichibansha, meaning first tea. Cool weather and slower early growth often help preserve amino acids in the shoots. The resulting teas may carry more sweetness and savory depth than leaves gathered after weeks of stronger summer light. A second crop, called Nibansha, can be harvested later in the summer. Some gardens also collect a third tea. Uji farms may therefore harvest 2 or 3 times during one growing year. Later leaves develop under warmer temperatures and brighter sunlight. They often contain a different balance of catechins and amino acids, giving the finished tea more bitterness and less of the soft character associated with the first spring crop. The method of picking also determines what enters the basket. Hand harvesting allows a worker to choose shoots by size and position. Fingers can leave behind damaged leaves, thick stems, and growth that has already become too coarse. This selectivity is especially useful for premium teas such as gyokuro or carefully made hand processes. Sencha. The work moves slowly. A person must reach across thousands of branch tips while keeping the harvested shoots from being crushed. Mechanical harvesters cover a much larger area. In many Japanese fields, cutting blades pass across the flat top of the tea hedge and collect the clipped material into bags or containers. The machines can gather leaves quickly enough to protect a large crop from changing weather. Their cutting line also brings in a wider mixture of buds, leaves, stems, and fragments. Careful sorting later removes some of that variation. The harvest remains biologically active after it leaves the field. Fresh tea leaves still contain living cells, water, sugars, enzymes, and oxygen. They continue to respire, meaning they use oxygen and release carbon dioxide while consuming stored energy. Heat can build inside a tightly packed basket or transport container. Bruising breaks cell compartments and allows enzymes to contact catechins that had been kept separate. Moisture loss begins at the leaf surface, while warm conditions speed many chemical reactions. A delay of several hours can change aroma, color, and the ease with which the leaves are later processed. Factories are therefore placed close enough to growing areas for the harvest to arrive quickly. Leaves are spread, ventilated, or moved in shallow loads to prevent crushing and excess heat. The tea maker can shape the chemistry from that point onward, yet the starting material has already been fixed by leaf age, season, sunlight, and the precision of the harvest. As soon as the shoot is cut, its enzymes begin directing the leaf toward further oxidation. Early heat is the step that interrupts that movement and preserves the path toward green tea. Inside an intact tea leaf, many reactive substances remain separated by thin cell walls and internal membranes. Catechins are stored in fluid-filled compartments called vacuoles. Enzymes involved in oxidation are located elsewhere in the cell. This separation allows the leaf to carry both materials without constantly transforming its own chemistry. Harvesting begins to disturb that arrangement. A clean cut damages cells near the stem, while transport can bend or bruise the softer leaf surfaces. Wilting removes water and makes the tissue more flexible. Rolling later breaks many more cells. As these barriers open, catechins meet enzymes and oxygen from the surrounding air. One important enzyme is polyphenol oxidase. It helps transfer electrons from T polyphenols to oxygen, starting a chain of reactions that creates new compounds. Peroxidase, another plant enzyme, can continue related changes by using naturally occurring peroxides. The process is called enzymatic oxidation because the leaf's own enzymes guide the reactions. Color begins changing as the chemistry moves forward. Fresh green pigments become less dominant, while new yellow, copper, and brown tones appear. Aromas that were faint inside the living leaf can grow stronger or change direction. The sharp, leafy character of the raw shoot gradually develops into the deeper scents associated with more oxidized tea. Black tea makers allow these reactions to continue for much longer before final drying. Some catechins join together and form the efflavins. The efflavins are orange-red compounds that contribute brightness, briskness, and part of the copper color seen in black tea. Further reactions produce larger, darker mixtures called the arubigins. These compounds add body reddish-brown color and much of black tea's deeper character. Oolong production interrupts oxidation at many different points. A lightly oxidized oolong may remain green and floral. A more heavily oxidized one can move closer to the warm color and fruit-like aroma of black tea. Green tea follows a much earlier interruption. Soon after the leaves reach the factory, tea makers apply enough heat to reduce the activity of polyphenol oxidase and other enzymes. This step is called fixation. It is also known as kill-green processing, a traditional name referring to the stopping of the leaf's active chemistry. Heat changes the three-dimensional shape of enzyme proteins. An enzyme works because its surface has a precise form that fits particular molecules. Once heating distorts that form, the enzyme can no longer guide the same reaction efficiently. Japanese green teas are commonly fixed with steam. The leaves may pass through a steaming machine within hours of harvest. Hot water vapor transfers heat quickly across the moist tissue and stops most oxidation, while preserving a strongly vegetal character. Sencha may develop notes compared with cut grass, seaweed, or cooked greens, depending on cultivar and steaming time. Many Chinese green teas use heated pans, drums, or rotating metal equipment. Direct contact with a hot surface removes moisture while deactivating enzymes. This drier style of heating can encourage warm aromas resembling toasted grain or chestnut. Longjing tea from Zhejiang province is a well-known pan-fired example. Both methods stabilize the leaf, though neither leaves it chemically identical to the moment of picking. Heat softens tissues, changes proteins, alters aroma molecules, and begins removing water. The term fermentation has often appeared in older descriptions of black tea. Its main transformation comes from enzyme-driven oxidation within the damaged leaf. True microbial fermentation involves bacteria, yeasts, or fungi, changing the material through their own metabolism. Some aged dark teas, including forms of pure air tea, do involve substantial microbial activity during processing or storage. That pathway differs from the rapid oxidation used to make ordinary black tea. Fixation therefore captures green tea at an early stage of its post-harvest change. Its catechin pattern remains closer to the fresh leaf. Its color stays greener, and its aroma follows a different path. The heated leaves are now stable enough to avoid becoming black tea. They are still soft, damp, bulky, and far too perishable for storage. Their next transformation will come through pressure, shaping, and the steady removal of water. After fixation, the tea leaves have stopped moving rapidly toward the chemistry of black tea. They have also become warm, limp, and heavy with water. A freshly harvested tea leaf is often close to 3/4 water by weight. Steaming adds surface moisture, while heat softens the cell walls and makes the leaf easier to bend without breaking into dry fragments. That water must be removed carefully. A leaf dried too quickly at high heat can scorch on the outside, while moisture remains trapped within it. A leaf stored while still damp can support mold, stale aromas, and unwanted chemical change. Rolling helps control that drying process. Pressure twists the leaf, compresses its tissues, and pushes internal moisture toward the surface. Some cells split open as the leaf is worked. The damage exposes substances that were previously held behind cell walls, which later allows hot water to reach them more easily. Rolling, therefore, affects the way tea dries and the way it brews. In traditional Japanese sencha production, the leaves pass through several stages of working and heating. Early movements handle a soft mass that can still cling together. Later rolling becomes firmer and more exact as the moisture level falls. The final shaping draws the leaves into narrow forms that resemble dark green needles. Modern factories use separate machines to imitate these older hand movements. One machine loosens and dries the steamed leaves. Another presses and rolls them. Later equipment straightens and tightens the material until the characteristic sencha shape appears. The finished geometry can reveal a great deal about how a tea was made. Longjing, a famous green tea from Zhejiang province in eastern China, is pressed and moved against a heated pan. Its dry leaves become broad, smooth, and flat. Skilled hand processing requires the tea maker to adjust pressure and motion as the leaves lose moisture. Too much force can tear them. Weak pressure may leave them unevenly shaped and difficult to dry. Gunpowder tea follows a different design. Its leaves are rolled into compact pellets, traditionally compared with small grains of gunpowder. The tight form protects the leaf during handling and reduces the amount of surface directly exposed to the air. When the pellets enter hot water, they loosen and slowly unfold. Curled teas can open into spirals, while twisted strips lengthen as their tissues absorb water. The shape changes how quickly the drink develops. A whole rolled leaf presents less exposed surface than a broken leaf. Water must move through the outer tissue before reaching much of the material inside. Broken tea releases soluble compounds more quickly because many internal surfaces are already open. Powder behaves faster still. Thousands of tiny particles make contact with the water at once. This can produce strong color, caffeine, catechins, and bitterness in a short brewing time. Tea bags often contain small leaf pieces, partly for this reason. They can create a noticeable infusion within a few minutes, even when the bag holds only a modest amount of tea. Tencha is an important exception to the rolling pattern. After steaming, tencha leaves are spread and dried without the repeated shaping used for sencha. They remain light, flat, and fragile. During later refining, coarse stems and larger veins are removed. The remaining leaf material can then be ground into matcha. Avoiding the rolling stage preserves a form suited to grinding, rather than whole leaf infusion. Drying continues until very little water remains. Finished tea commonly contains only about 3 to 5% moisture by weight. At this level, microorganisms have difficulty growing because too little free water is available for their cells. Scientists describe this usable moisture as water activity. A food may contain some water, while still having water activity low enough to slow mold and bacteria. Dry tea can nevertheless continue changing during storage. Oxygen reacts slowly with pigments and aroma compounds. Heat speeds those reactions. Light can damage sensitive molecules, while moisture absorbed from humid air can soften the leaves and encourage staling. Tea also absorbs nearby odors easily. A poorly sealed package stored beside spices, soap, or strong food may carry those smells into the cup. Good storage therefore uses an airtight container kept away from heat, direct light, and damp air. The finished leaf now holds a physical record of its treatment. Its cells carry the marks of pressure. Its surface reflects the method of heating. Its shape controls how water will enter it later. By varying sunlight before harvest and force after it, tea makers can turn one species into needles, flat blades, curled leaves, compact pellets, or powder. Green tea has become a family of distinct forms, each built from a different combination of growth and processing. The shapes created during rolling and drying lead into a much wider family of teas. Sencha provides a useful starting point. Its leaves usually grow in open sunlight before being steamed, rolled, shaped, and dried. The finished tea often appears as narrow green needles that soften and open during brewing. A small change in steaming time can produce a noticeably different result. Deep steamed sencha, known as fukamushi sencha, may remain in steam for roughly 2 to 3 times longer than ordinary sencha. The extra heat softens the leaf tissue more deeply. Fragile leaves break into smaller pieces during later rolling, so the dry tea often contains fine particles. Those particles enter the water quickly and create a darker, cloudier infusion with a strong green color. Pre-harvest shading changes the plant before processing begins. Kabusecha is covered for a shorter period than gyokuro, often around 1 to 2 weeks. Reduced sunlight slows some chemical changes in the growing shoot and helps preserve amino acids that contribute sweetness and savory flavor. Gyokuro receives a longer period of shade, traditionally more than 20 days. Its harvested leaves are then steamed and rolled into thin shapes, much like other fine Japanese leaf teas. The finished gyokuro remains a whole leaf infusion. Hot water draws soluble compounds from the leaves, while most of the plant material stays behind in the teapot. Tencha begins with shaded leaves as well, but its path changes after steaming. The leaves are dried flat instead of being repeatedly rolled. During refining, stems and thicker veins are removed. The remaining soft leaf material is ground between stone surfaces to make matcha. Because matcha is a powder, the drink contains suspended leaf particles. The drinker consumes those particles along with the dissolved caffeine, amino acids, and catechins released into the water. Bancha shows how harvest age can create another style. It is often made from larger, more mature leaves collected after the mainspring harvest. Those leaves contain more fiber and usually produce a simpler, stronger character than the youngest shoots used for premium sencha. Further heating can transform a finished green tea again. Hojicha is made by roasting processed tea, often bancha or stems, at high temperature. Roasting changes the leaf from green toward reddish-brown and creates toasted aromas through heat-driven chemical reactions. The cup may suggest roasted grain, wood, or caramel, depending on the material and temperature used. Genmaicha combines green tea with roasted rice. The rice adds a warm, cereal-like aroma and softens the sharper parts of the tea. Some mixtures include pieces of puffed rice, though the pale grains do not all puff in the same way. Chinese green teas reveal another set of choices. Longjing from Zhejiang province is heated and pressed against a hot surface until its leaves become broad and flat. Biluo Chun, traditionally associated with Jiangsu province, is shaped into fine curls covered with pale leaf hairs. Gunpowder tea is rolled into compact pellets that loosen and unfurl in hot water. These names describe traditions rather than perfectly uniform products. Cultivar, harvest date, weather, factory equipment, and the skill of the tea maker can produce large differences within one named style. Matcha has moved especially far beyond the tea bowl because powder mixes easily into other foods. It now appears in milk drinks, noodles, cakes, ice cream, sauces, and filled confections. A sweet matcha latte may contain substantial sugar and milk. A cookie may carry only a small amount of powder. Those foods provide a different nutritional exposure from unsweetened matcha whisked with water. Across all these forms, the same plant is being redirected through light, leaf age, steam, pressure, roasting, blending, and grinding. Their dry appearances may range from needles to flat blades, curled threads, brown fragments, or bright green powder. Each remains unfinished until water enters the leaf or surrounds its particles and begins selecting which molecules will move into the cup. The dry leaf changes again as soon as water reaches its surface. Tiny spaces within the rolled tissue begin filling with liquid. Heat softens the leaf, while water moves through cracks, pores, and cells open during processing. Compounds that can dissolve in water begin leaving the plant tissue. This movement is partly driven by diffusion. Diffusion occurs when molecules spread from an area where they are more concentrated into an area where they are less concentrated. Inside the wet leaf, caffeine and catechins may be present at much higher concentrations than they are in the surrounding water. They gradually move outward until the difference becomes smaller. Each compound follows its own pace. Caffeine dissolves readily in hot water. Amino acids, such as L-theanine, can enter the infusion fairly quickly. Many catechins require more time or heat, especially when they remain protected inside larger leaf pieces. Aroma molecules may escape into the air within seconds, which is why the scent above a cup can change before the tea is ready to drink. The amount of leaf controls how much material is available for extraction. Water volume determines how widely those compounds are diluted. A small amount of water poured over several grams of tea can create a concentrated infusion. The same leaves placed in a large pot may produce a lighter result, even when the temperature and brewing time remain unchanged. Particle size changes the speed. A whole rolled leaf has relatively little exposed surface. Water must move inward before reaching much of its internal material. Broken leaves present more open edges. Fine tea bag particles release color, caffeine, and bitterness quickly because water touches thousands of exposed surfaces at once. Agitation can speed the process as well. Stirring, whisking, or repeatedly pouring water across the leaves replaces the concentrated liquid near their surfaces with fresher water. Repeated infusions draw out new portions of the remaining compounds. The first brew may carry strong aroma and readily soluble material. Later brews can reveal compounds that require more time to leave the softened leaf. Water chemistry also shapes the cup. The pH scale describes how acidic or alkaline a liquid is. Minerals, such as calcium and magnesium, can interact with tea compounds and alter clarity, color, and flavor. Very hard water may produce a duller infusion or a thin film at the surface. Water containing few minerals can produce a brighter taste, though extremely pure water may seem flat because some dissolved minerals help carry flavor. Temperature has one of the clearest effects. Hotter water moves more quickly at the molecular level. It enters the leaf faster and usually dissolves more material within the same amount of time. That can release a rich aroma and strong flavor. It can also bring out catechins and caffeine rapidly enough to create harsh bitterness or a drying sensation. No single temperature works perfectly for every green tea. Leaf size, cultivar, steaming depth, storage, and personal preference all change the result. A controlled experiment using Turkish green tea offers one clear example. Researchers brewed the tea at 75, 85, and 95 degrees Celsius. They tested 8 brewing times, beginning at 1 minute and extending to 45 minutes. For that particular tea, 85 degrees Celsius for 3 minutes produced the highest measured concentration of EGCG. The amount reached 50.69 milligrams per 100 milliliters. A sensory panel also gave this preparation the strongest overall ratings. Those results belong to the tea and conditions tested in that experiment. A delicate Japanese gyokuro, or a heavily broken tea, could respond differently. The longest and hottest brews in the study became very dark and intensely bitter. Panel members rated them poorly, even though the water had extracted large amounts of leaf material. More extraction, therefore, does not guarantee a more pleasant cup. Heat and time can also change the compounds after they enter the water. Some tea catechins have structures known as epiforms. During prolonged heating, part of this structure can rearrange through a process called epimerization. The molecule keeps the same basic ingredients while adopting a different three-dimensional arrangement. In the experiment, some common epicatechins decreased during long, hot brewing as related forms increased. A cup is therefore shaped by extraction and chemical change occurring together. Leaf tea remains an infusion. Water removes soluble compounds, while most of the plant's fiber and solid tissue stays in the pot. Matcha behaves differently because the powder remains suspended in the drink. Its particles may settle slowly, yet they are swallowed along with the liquid. This changes the physical form and can increase the amount of leaf material consumed. A few ordinary choices involving temperature, time, leaf size, and water quietly decide which parts of the plant reach the cup. Once those molecules arrive, the tongue, nose, saliva, and surfaces of the mouth turn chemistry into bitterness, sweetness, aroma, savoriness, and dryness. Once the extracted molecules reach the mouth, several sensory systems begin working together. Taste comes from receptors on the tongue and elsewhere in the mouth that respond to basic qualities such as sweetness, bitterness, sourness, saltiness, and savoriness. Aroma follows a different route. Volatile organic compounds rise from the warm liquid and enter the nose. Some travel through the nostrils during inhalation. Others move upward from the back of the mouth while the tea is being swallowed. Smell receptors then help create impressions such as grass, flowers, citrus peel, toasted grain, or seaweed. The drying sensation left by strong tea belongs mostly to touch. It is called astringency. Astringency can feel rough, puckering, or slightly tight across the tongue, gums, and inner cheeks. Green tea produces all of these sensations through a mixture that includes polyphenols, caffeine, amino acids, chlorophyll, and volatile compounds. Caffeine activates bitter taste receptors. Catechins also contribute bitterness, especially when large amounts are extracted by hot water or long brewing. EGCG is one of the catechins strongly associated with both bitterness and astringency. The dry feeling develops through an interaction with saliva. Saliva contains proteins that coat the mouth and help its surfaces move smoothly across one another. Tea polyphenols can attach to some of those proteins. The resulting groups may clump together or become less effective as lubricants. Friction between oral surfaces then increases, creating the rough sensation that remains after the liquid has passed. Astringency, therefore, differs from bitterness, even though the two often arrive together. Bitterness is detected by taste receptors. Astringency develops partly from a physical change in lubrication. Amino acids soften the experience. L-theanine can contribute a mild sweetness and a rounded savory quality. Glutamate and related compounds also support umami, the basic taste associated with broths, mushrooms, seaweed, and aged foods. The balance among amino acids, catechins, and caffeine helps explain why one green tea may seem gentle, while another tastes sharp. Aroma adds far more variation than the 5 basic tastes alone could provide. Fresh or lightly steamed tea may contain volatile compounds that suggest cut grass, green vegetables, flowers, or marine air. Pan firing encourages warmer impressions such as chestnut and toasted grain. Roasting creates another aromatic direction through reactions that occur under stronger dry heat. Hojicha may therefore smell nutty or caramel-like, even though it began as green tea. Cultivar influences which aroma compounds the leaf can produce. Harvest season changes the balance because temperature and sunlight affect plant metabolism. Storage matters as well. Oxygen can slowly reduce fresh aromas and create flatter or stale notes. Tea kept near heat or moisture changes faster than leaves sealed in a cool, dry container. Shade cultivation alters flavor before the leaf is picked. Gyokuro and tencha are covered during shoot development, while most sencha grows under open sunlight. Lower light changes the way the plant handles nitrogen and carbon. More free amino acids tend to remain in shaded shoots, including L-theanine. Catechin production may shift, and the leaves increase chlorophyll as they try to capture the limited light available. This gives many shade-grown teas a deep green appearance and a strong savory character. Gyokuro carries those qualities into an infused leaf tea. Tencha follows a separate processing path and becomes matcha after refining and grinding. Color can provide useful clues about cultivation and processing. It cannot measure medical strength. A dark green powder may contain abundant chlorophyll, yet color alone does not reveal how much caffeine, or EGCG, reaches the body. A cloudy infusion may result from tiny leaf particles rather than unusually high quality. A pale tea can still contain substantial aroma and dissolved compounds. Sensory experience depends on the full mixture, along with the temperature and concentration of the cup. The tongue detects bitter compounds. Saliva changes the feeling of astringency. Volatile molecules shape the aroma reaching the nose. Together, these signals create what people casually describe as the green taste of green tea. Two important members of that mixture continue beyond the mouth. Caffeine and L-theanine are absorbed, transported through the bloodstream, and eventually influence activity within the nervous system. After green tea is swallowed, caffeine passes through the stomach and small intestine into the bloodstream. Circulation carries it throughout the body, including toward the brain. There, caffeine can cross the blood-brain barrier, a protective layer that limits which substances can leave the blood and enter brain tissue. Its best understood action involves adenosine. Adenosine is a signaling molecule produced as cells use energy. During many hours of waking activity, its influence gradually increases. Adenosine attaches to specialized receptors and helps reduce neural activity, contributing to the growing pressure to rest. Caffeine has a shape that allows it to occupy some of those same receptors. While caffeine sits there, adenosine has less opportunity to deliver its usual signal. The result can include greater alertness and a temporary reduction in perceived tiredness. This effect comes from changing how the nervous system receives a fatigue-related message. The body continues using energy, and the adenosine signal can become noticeable again as caffeine is broken down. L-theanine follows a separate chemical path. It is a non-protein amino acid, meaning the plant produces it without using it as one of the standard building blocks assembled into most proteins. Tea contains far more L-theanine than most common foods. After absorption, it can reach the brain and may influence several signaling systems involved in attention, stress responses, and mood. Researchers have also studied changes in patterns of electrical brain activity after isolated doses. These findings help support green tea's reputation for producing calm alertness, especially when L-theanine appears beside caffeine. The reputation has a plausible biological basis, though the size and reliability of the effect remain uncertain. A systematic review published in 2025 examined 50 randomized controlled trials. In a randomized trial, participants are assigned by chance to different treatments, helping researchers reduce the influence of pre-existing differences between the groups. Only 15 of the 50 trials contained results suitable for inclusion in at least one meta-analysis. A meta-analysis combines compatible findings from several studies to estimate an overall effect. The small usable group reflects an important problem in this research. Different trials used different doses, testing methods, participant groups, and combinations of compounds. Some gave L-theanine alone. Others paired it with caffeine. Testing could occur after one dose, over several days, or following longer periods of regular use. Several attention measures showed small to moderate differences favoring combined L-theanine and caffeine during the first 1 or 2 hours after consumption. These included reaction time, vigilance, and the ability to switch attention between tasks. Some mood measures also showed possible improvement. Results varied across studies, and many confidence intervals were wide. A confidence interval is a calculated range showing where the true effect may reasonably lie. A wide interval means the data allows several possibilities, including an effect too small to matter in ordinary life. Some intervals also cross the point representing no clear difference between treatments. The controlled doses used in these trials deserve careful attention. A capsule containing a measured amount of purified L-theanine and caffeine differs from a cup made with loose censure. The tea's cultivar, harvest season, leaf quantity, brewing temperature, and steeping time all affect its chemical content. Commercial matcha may deliver suspended leaf particles, while an ordinary infusion leaves most solid tissue behind. Milk, sugar, food, and the speed of drinking can further change the experience. Evidence from an isolated dose, therefore, cannot automatically describe a particular cup prepared at home. The same caution applies to sleep. Green tea usually contains caffeine unless it has been decaffeinated. L-theanine may influence relaxation or attention, yet it does not remove caffeine from the drink. A cup taken late in the evening can still delay sleep or make sleep lighter in a sensitive person. The outcome depends on the dose and the time of day, along with age, habitual caffeine use, medications, and individual metabolism. Frequent caffeine users may feel a weaker alerting effect than someone who rarely consumes it. Some people can drink tea near bedtime without noticing a problem. Others remain affected for many hours after a modest serving. Caffeine reaches the nervous system through a relatively direct and well-studied route. The catechins linked with many longer-term health claims face digestion, chemical breakdown, limited absorption, and rapid metabolism before they can influence distant tissues. The catechins in green tea are often introduced with a single familiar word: antioxidants. That label describes a real chemical property, though it can hide much of the biology underneath it. Oxidation is a process involving the movement of electrons between atoms or molecules. Electrons are tiny charged particles that take part in chemical bonds and reactions. Human cells depend on electron transfer every moment. It helps release usable energy from food and supports many reactions needed for life. These processes can also produce reactive oxygen species. Reactive oxygen species are oxygen-containing molecules that readily react with nearby material. Some are free radicals, meaning they carry an unpaired electron that makes them especially reactive. Mitochondria, the structures that help cells release energy, generate small amounts during ordinary metabolism. Immune cells deliberately produce reactive molecules to damage invading microorganisms. Controlled amounts also participate in communication between cells and help regulate growth, blood flow, and responses to injury. Problems can develop when reactive oxygen species accumulate faster than protective systems can manage them. This imbalance is called oxidative stress. Under those conditions, reactive molecules may alter fats in cell membranes, damage proteins, or affect DNA. Cells contain several layers of protection. Enzymes, such as superoxide, dismutase, and catalase, convert reactive molecules into less harmful forms. Small compounds made by the body, including glutathione, also help control them. Food supplies additional substances that can participate in this larger system. Removing every reactive oxygen species would disrupt normal signaling and immune defense. Healthy biology depends on regulation rather than complete elimination. Tea polyphenols include the catechins introduced earlier. The best known is EGCG, which means epigallocatechin gallate. Researchers often study it because the molecule can interact with reactive chemicals under controlled conditions. It may also bind to proteins, affect cell membranes, alter enzyme activity, and influence signaling pathways inside cells. A laboratory test can measure how well EGCG reacts with a selected chemical in a tube or dish. The result may be reported as antioxidant capacity. That measurement shows what happened under those exact conditions. It does not establish that drinking green tea prevents cancer, heart disease, or another specific illness. Living bodies create a much more complicated environment. A compound must survive digestion, cross the intestinal wall, enter circulation, and reach the relevant tissue in a useful form. Its concentration also matters. Cells in an experiment may be placed directly in a solution containing much more EGCG than ordinary tea drinking can deliver to human tissue. The exposure can begin immediately and remain tightly controlled. A person drinking tea receives a changing mixture that passes through the digestive tract and is transformed along the way. The intestinal wall and liver attach chemical groups to many catechins. These changes help the body transport or remove them, while also producing forms that behave differently from the original molecule. Only a limited fraction of unchanged EGCG may enter circulation after a normal serving. Food, dose, timing, and individual metabolism can alter that amount. This helps explain why impressive test tube results may lead to smaller or inconsistent findings in people. Human trials sometimes measure compounds linked with oxidative stress, rather than waiting years for disease outcomes. Researchers may examine damaged fats, antioxidant enzyme activity, or other biological markers before and after tea consumption. Results have varied. Some studies report favorable changes in certain markers, while others find little clear difference. The chosen tea, study length, participant health, and laboratory method can all influence the outcome. Catechins may also act through routes that extend beyond directly neutralizing reactive molecules. They can influence enzymes involved in inflammation. Interactions with proteins may alter signals controlling how cells respond to stress. Gene expression can change when chemical signals affect which instructions a cell reads from its DNA. These possible actions depend on the tissue, dose, chemical form, and timing of exposure. The image of antioxidants forming a simple shield around cells, therefore, leaves out most of the process. EGCG begins as one compound within a complex leaf. Its behavior inside the body depends on where it travels, what it becomes, and how much reaches a particular location. Following that journey through digestion, liver metabolism, and the intestinal microbiome reveals why the chemical promise of green tea becomes less predictable after a person drinks it. The first biological filters appear within minutes of swallowing the tea. Catechins enter the stomach mixed with water, caffeine, amino acids, and hundreds of smaller plant compounds. Their exact starting dose depends on the tea style, leaf quantity, particle size, water temperature, and brewing time. Food already present in the stomach changes the chemical surroundings. Acidity, digestive fluids, minerals, proteins, and fats can influence how stable the catechins remain and how easily they later reach the intestinal wall. Most absorption occurs farther along in the small intestine. Its inner surface is covered with millions of tiny projections called villi. These structures greatly increase the area available for nutrients and other compounds to cross into the body. Catechins reach this surface in several forms, yet only part of the swallowed amount enters circulation. This limited entry is described as low bioavailability. Bioavailability means the proportion of a consumed substance that reaches the bloodstream in a form available to the body. Individual catechins differ in how readily they cross the intestinal lining. EGCG is a relatively large molecule and is absorbed less efficiently than caffeine. Some catechins also break down or rearrange before absorption, especially when the chemical environment becomes less acidic. The intestinal wall begins changing the molecules that do enter. Special enzymes can attach small chemical groups to them. Methylation adds a small carbon-containing group, called a methyl group. Glucuronidation attaches glucuronic acid, a substance the body uses to make many compounds easier to transport and remove. Sulfation adds a sulfate group. These reactions are called conjugation. They often increase a molecule's ability to travel in watery fluids and help determine how quickly it is cleared through urine or bile. The liver performs more of the same work after blood from the intestine arrives through the portal vein. As a result, distant tissues may encounter methylated, glucuronidated, or sulfated catechin derivatives rather than large amounts of unchanged EGCG. A derivative is a chemically altered version of the original compound. Its behavior can differ in important ways. It may enter cells less easily, bind to different proteins, or remain in circulation for a different length of time. The portion that is never absorbed continues toward the large intestine. There, the colon contains a dense community of bacteria and other microorganisms known as the gut microbiome. Many microbes possess enzymes that human cells do not. They can break the larger catechin structures into smaller compounds, including several phenolic acids. Some of these microbial products cross the colon wall and enter circulation later. This means that the effects of tea may come partly from molecules created hours after drinking, following work performed by intestinal microbes. Microbiomes vary greatly between people. Diet helps determine which species are abundant. Recent antibiotics can remove or suppress parts of the community. Age, geography, illness, and long-term eating habits also shape its composition. Two people drinking the same tea may therefore produce different mixtures of microbial metabolites. Genetic differences can alter digestive enzymes and transport proteins. Liver health affects the speed of chemical processing. Medications may compete for some of the same metabolic pathways. A tea consumed with breakfast creates a different exposure from an extract taken while fasting. Dose and physical form add further variation. A brewed infusion delivers compounds that dissolved into the water. Most leaf fiber and insoluble material remain in the pot. Matcha contains suspended particles, so the drinker consumes more of the ground leaf itself. A matcha cake or sweetened latte may contain only a modest amount of powder beside flour, milk, sugar, or fat. Bottled green tea can lose catechins during storage and may include acids, flavorings, or substantial sweetener. Concentrated extracts can supply catechin doses equal to several cups within a small capsule. These formats share a plant origin while creating very different exposures. The body receives each one through digestion, chemical conversion, microbial breakdown, and removal. By the time tea compounds reach the bloodstream, the original leaf chemistry has been filtered into a smaller and more varied collection. Human health claims can therefore be judged most reliably through measured outcomes in people, where absorption, metabolism, dose, and daily life are already part of the result. Once tea compounds have passed through digestion and metabolism, researchers can measure what changes inside real people. Heart health covers several separate outcomes. Blood pressure records the force of blood against artery walls. Cholesterol measurements describe fats carried through the bloodstream in particles called lipoproteins. Low-density lipoprotein, usually shortened to LDL, transports cholesterol toward tissues and is associated with artery disease when levels remain high. High-density lipoprotein, called HDL, carries some cholesterol back toward the liver for processing. Triglycerides are another form of circulating fat. Researchers may also examine how well blood vessels widen, along with chemical markers connected with inflammation. A tea study can improve one measurement while leaving the others unchanged. Reviews summarized by the National Center for Complementary and Integrative Health have found small reductions in total cholesterol and LDL cholesterol among people consuming green tea or green tea preparations. The reported decreases are generally around 2 to 5%. For a person with an LDL level of 150 milligrams per deciliter, a 5% reduction would equal about 7.5 milligrams per deciliter. That change can be measured, though it is far smaller than the reductions often produced by cholesterol-lowering medication. Findings for HDL cholesterol have been inconsistent. Triglyceride results also vary, with many studies showing little clear change. Blood pressure trials tell a similar story. Pressure is measured in millimeters of mercury, written as mmHg. The upper number, called systolic pressure, measures force while the heart contracts. The lower number, called diastolic pressure, reflects pressure while the heart relaxes between beats. Meta-analyses of randomized trials have reported average reductions of only a few millimeters of mercury after green tea interventions. A shift this small may still matter across a population containing millions of people. For one person with diagnosed hypertension, it remains too modest and uncertain to replace prescribed care. Randomized trials are useful because participants receive an intervention by chance. Researchers can compare green tea with a control drink or placebo over a defined period. These studies are often short and focus on risk markers such as cholesterol or blood pressure. They rarely continue long enough to observe large numbers of heart attacks or deaths. Long-term cohort studies approach the issue differently. A prospective cohort enrolls people, records their habits, and follows them forward through time. In 2024, a meta-analysis combined 38 prospective cohort datasets reported. Across 27 papers, together they included 1,956,549 participants. Moderate tea intake was associated with lower all-cause mortality, meaning fewer deaths from any cause during follow-up. It was also associated with lower cardiovascular mortality. The scale of this analysis gives the pattern statistical weight. Its design still cannot prove that tea alone caused the difference. Participants were never randomly assigned to drink tea for several decades. Regular tea drinkers may smoke less, exercise more, or eat differently from people who rarely drink it. Income can influence food quality and access to healthcare. Alcohol use, education, existing illness, and cultural routines can also differ between groups. Researchers adjust their calculations for many of these factors, though no statistical method can perfectly measure every habit across a lifetime. The beverage being replaced matters as well. A person who chooses unsweetened green tea instead of a sugar-sweetened soda avoids the sugar and calories in the soda. That substitution could improve long-term health, even if no catechin directly changes an artery. Tea served with several spoonfuls of sugar creates a different comparison. The hard evidence therefore points toward modest possible benefits rather than dramatic protection. Short-term trials suggest small changes in certain risk markers. Large cohorts find encouraging associations over many years. Green tea remains a beverage within a broader pattern of diet, activity, medical care, and inherited risk. The same discipline becomes even more important when green tea is sold with a stronger promise that it can make body fat disappear. Green tea's connection with body weight begins with a real, measurable effect of caffeine. After caffeine blocks adenosine receptors, nervous system activity can increase for several hours. This may raise alertness and slightly increase energy expenditure, meaning the body uses a little more energy than it would at rest. The temporary rise is often described as thermogenesis. Thermogenesis means producing heat through metabolism. Caffeine can also increase the release of signaling chemicals such as norepinephrine. Norepinephrine helps prepare the body for activity and can encourage stored fat to release fatty acids into the bloodstream. Those fatty acids may then be used as fuel. Green tea catechins have been studied alongside this pathway. Some laboratory research suggests that EGCG can affect an enzyme called catechol-O-methyltransferase. This enzyme helps break down norepinephrine and related signaling molecules. Slowing that breakdown could, in theory, extend part of the metabolic signal. Catechins have also been examined for possible effects on fat digestion, intestinal absorption, and the amount of fat used during activity. These mechanisms are biologically plausible. Their practical size remains limited. A temporary increase in energy use is small compared with the energy stored in body fat or consumed across an entire day. The body also adapts to repeated caffeine exposure. Someone who drinks caffeinated beverages every day may develop tolerance, meaning the same dose produces a weaker effect than it did at first. Weight change depends on energy balance over weeks and months. When energy intake repeatedly exceeds the amount used, the excess can be stored. A small metabolic increase from caffeine cannot reliably overcome a sustained surplus created by meals, snacks, and sweetened drinks. Many studies used to support weight loss advertising have tested concentrated extracts rather than ordinary brewed tea. A standardized extract may deliver several hundred milligrams of catechins in one capsule. Some preparations also contain a measured caffeine dose. Commercial weight loss mixtures may add guarana or other stimulants, making it difficult to identify which ingredient produced an effect. Catechin-caffeine combinations have been studied more often than catechins alone. This matters because a cup of lightly brewed green tea may deliver a much smaller dose than a research capsule. Tea style, leaf quantity, brewing temperature, and steeping time create further variation. A trial involving a concentrated extract, therefore, does not automatically predict what will happen after one daily cup of sencha. Reviews summarized by the National Center for Complementary and Integrative Health describe the average effect of green tea catechins and caffeine on body weight as modest. Some trials report a small reduction in body mass or waist measurement. Others find little meaningful difference from a placebo. Even when a result reaches statistical significance, the physical change may remain minor. Statistical significance means the observed difference is unlikely to be explained entirely by random variation under the assumptions of the analysis. It does not show that the difference is large enough to notice in daily life. Green tea also cannot choose where stored fat is removed. Changes in abdominal fat depend on total weight change, hormones, genetics, age, and patterns of fat storage throughout the body. The idea of detoxing fat cells has no clear biological meaning. The liver, kidneys, lungs, and digestive system continuously process and remove many waste products. Tea does not wash stored body fat clean. Its most useful weight-related role may occur through beverage replacement. A large sweetened soft drink can contain several hundred calories. Specialty coffees may include syrups, whipped toppings, or large amounts of milk and sugar. Juice also supplies energy quickly, even when it contains vitamins. Replacing one of those drinks with unsweetened green tea can remove a substantial amount of daily energy intake. That reduction comes mainly from the beverage no longer consumed. The tea may still provide caffeine, aroma, warmth, and a satisfying routine without added sugar. For some people, that ordinary substitution could matter more over time than the small rise in thermogenesis measured after caffeine. Green tea can fit comfortably within a long-term eating pattern. Its average direct effect on body weight remains too small and inconsistent to make it a primary weight loss treatment. Claims involving cancer prevention or a longer life demand even more careful separation between laboratory mechanisms, population patterns, and proven human outcomes. Cancer research became interested in green tea because catechins can influence several processes involved in abnormal cell growth. In laboratory dishes, EGCG has affected proteins that help cells divide, respond to stress, and communicate with nearby tissue. Researchers have also observed changes in inflammation-related pathways and oxidative reactions. Under some experimental conditions, catechins can encourage apoptosis. Apoptosis is an organized process through which a damaged or unnecessary cell dismantles itself. Cancer cells often develop ways to resist these internal controls. A compound that restores part of that response can appear promising during an early experiment. Cultured cells provide a simplified environment. Researchers select one cell line, prepare a measured concentration, and expose the cells for a chosen number of hours. The compound reaches them directly. A tumor inside a person exists within a far more complicated setting. It may receive blood from newly formed vessels and interact with immune cells, hormones, connective tissue, and nearby organs. The liver may transform a swallowed compound before it reaches the tumor. Kidneys may begin removing it. while proteins in the bloodstream can change how much remains free to act. The dose used in a dish may also exceed the concentration human tissue can reach. After several cups of tea. Animal studies add whole-body biology. They allow researchers to observe digestion, circulation, immune responses, and tumor growth within a living organism. Some experiments have found slower tumor development after animals received green tea catechins. Translation into ordinary human tea drinking remains uncertain. Laboratory animals may receive concentrated extracts through food, water, injection, or a tube placed into the stomach. The dose per kilogram of body weight can be far higher than a person receives from brewed tea. Some models also use implanted tumors or specially bred animals with altered cancer risk. These methods help test mechanisms, though each model represents only part of human disease. Cancer includes many diseases arising from different tissues and genetic changes. A substance associated with one type of cancer may show no useful relationship with another. Breast cancer, colorectal cancer, liver cancer, and leukemia follow different biological paths. Smoking can strongly alter studies of lung or digestive cancers. Hormones, infections, inherited mutations, and age may influence other sites. Human observational studies have therefore produced a mixed picture. Some report lower rates of a particular cancer among people who drink more green tea. Others find no clear association after accounting for smoking, diet, and other habits. Results have varied by country, sex, intake level, cancer site, and study design. Clinical evidence has not established green tea as a general cancer preventive or cancer treatment. Cell and animal experiments support biological plausibility. They show that a mechanism could exist under selected conditions. Clinical proof requires evidence that realistic exposure improves meaningful outcomes in people. The same separation applies to longevity. The mortality analysis described earlier combined 38 prospective cohort datasets and nearly 2 million participants. Moderate tea intake was associated with lower all-cause and cardiovascular mortality during follow-up. Researchers could adjust their calculations for measured factors such as age, smoking, alcohol use, exercise, and existing illness. Unmeasured differences still remain possible. Tea drinkers may follow different meal patterns, replace sugary beverages, or seek medical care more regularly. Income and education can influence both beverage habits and long-term health. A cohort can reveal that two patterns travel together. It cannot show with certainty that tea itself added years to the participants' lives. Green tea can still belong comfortably within a varied dietary pattern. An unsweetened cup provides fluid and flavor with very little energy. Its use should remain separate from medical treatment. Cancer screening can identify disease before symptoms appear. Vaccination can prevent infections linked with several cancers. Medical evaluation determines whether a concerning change requires testing. Surgery, radiation, and prescribed medicines have roles supported by evidence for specific diagnoses. Tea cannot safely replace any of these measures. The responsible conclusion rests between exaggeration and dismissal. Green tea contains compounds worthy of study, and some population findings remain encouraging. Current evidence does not justify a general claim that the drink prevents cancer, cures existing disease, or guarantees a longer life. The physical stakes rise further when manufacturers remove tea from the ordinary cup and compress the catechins from many servings into a single concentrated capsule. The amount of tea swallowed can change far more than the strength of its flavor. During ordinary brewing, water removes only part of the caffeine, catechins, and amino acids held inside the leaf. Most plant fiber remains in the teapot or tea bag. A supplement follows a different design. Manufacturers can extract catechins from large quantities of leaves, purify the mixture, and place a standardized dose into one tablet or capsule. That dose may enter the stomach within seconds, sometimes when no food is present to slow absorption. Brewed green tea is generally considered safe for most adults when consumed in moderate amounts. Its caffeine can still cause unwanted effects. A sensitive drinker may experience restlessness, a racing heartbeat, digestive discomfort, or difficulty sleeping. Serving size and brewing method matter, because a large mug of strongly brewed tea can contain much more caffeine than a small, lightly prepared cup. Concentrated extracts create a different safety problem. Uncommon cases of liver injury have been linked mainly with green tea extract products, particularly tablets and capsules. Reports have included inflammation of the liver and increases in liver enzymes measured through blood tests. Symptoms can include nausea, unusual tiredness, abdominal discomfort, dark urine, or yellowing of the skin and eyes. Most people using these products do not develop liver injury. The reports remain important because severe cases have occasionally required hospital care. Fasting may increase exposure by allowing a concentrated dose of EGCG to be absorbed more rapidly. Individual susceptibility also varies. Genetics, liver function, other supplements, medication use, and the exact composition of the product may all influence risk. The European Food Safety Authority reviewed evidence from brewed tea and concentrated products. It found no general liver safety concern from traditional green tea infusions. Supplement intake at or above 800 milligrams of EGCG per day was associated with early signs of liver damage in some studies. That threshold refers to supplemental EGCG rather than the amount normally obtained from a few cups of brewed tea. Product labels can still be difficult to interpret. One capsule may list total green tea extract without clearly stating how much EGCG it contains. Another may provide the catechen amount per serving, while defining a serving as several capsules. Quality and purity can also differ between manufacturers. Tea compounds may interact with medications by changing absorption, transport, or metabolism. The possible combinations are too numerous for one universal list. People using prescription medicine face a different decision from someone choosing an occasional cup, especially when considering concentrated extracts. A pharmacist or medical professional can check the specific medicine and dose involved. Polyphenols also interact with nutrients. Non-heme iron is the form found mainly in plant foods, fortified grains, and many supplements. Tea polyphenols can bind to this iron inside the digestive tract, making part of it harder to absorb. The effect is strongest when tea is consumed with the meal containing the iron. For a person with healthy iron stores, an occasional cup with food may have little practical importance. Someone with iron deficiency, heavy blood loss, or a largely plant-based diet may need to separate tea from iron-rich meals. Green tea ingredients can also appear in regulated medicine. A prescription ointment containing standardized tea catechins, known as sinecatechins, has been tested and approved for a defined topical use. It is applied directly to specific external skin lesions in a measured concentration. Its existence does not show that drinking green tea treats the same condition. A food, a supplement, and a drug follow different routes through testing, regulation, dosing, and delivery. The word natural identifies where an ingredient began. It gives no measurement of concentration or purity and reveals nothing about interaction risk. Safety emerges from the dose, chemical form, route of delivery, timing, metabolism, and the person receiving it. Once brewed tea has been separated from high-dose extract, green tea returns to its original scale as a cultivated leaf. Its future now depends on rainfall, temperature, soil, pests, and whether tea-growing regions can adapt to a changing climate. Every future cup still begins with a perennial evergreen shrub, sending out a fresh flush of shoots. The plant may remain in the ground for decades, yet each harvest depends on conditions changing from week to week. Tea prefers acidic soil, dependable moisture, and temperatures that support steady growth without prolonged heat stress. Workers must prune the bushes, manage weeds, watch for pests, and collect new shoots during a narrow stage of development. Climate influences how often those shoots appear and what chemistry they carry. Higher temperatures can accelerate growth for a time. Extended heat may also shorten the period in which tender leaves develop their preferred balance of amino acids, catechins, caffeine, and aroma compounds. Drought slows shoot expansion and reduces the water available for photosynthesis. Excessive rain can waterlog roots, erode slopes, interrupt harvesting, and increase fungal disease. Altered cloud cover changes how much sunlight reaches the leaf. That shift affects chlorophyll, L-theanine, and the catechins that contribute bitterness and astringency. Insects also respond to changing conditions. Warmer winters can allow more pests to survive until spring. Some species may spread into elevations or regions that were previously too cool. Growers may then face more feeding damage during the brief period when valuable young shoots are opening. A systematic review of climate and tea production identified 42 studies that examined effects on yield. One analysis from Assam found that monthly temperatures above 26.6 degrees Celsius were associated with declining production. At an average monthly temperature of 28 degrees Celsius, an additional rise of 1 degree was linked with an estimated yield reduction of 3.8%. A few percent may sound small within a single field. Across thousands of hectares and repeated harvests, the missing leaves can affect factory schedules, worker income, export supply, and the price paid for finished tea. The effects will vary across regions. A cool location may gain a longer growing season as average temperatures rise. Higher elevations could remain suitable after warmer lowlands become less dependable. Elsewhere, heat may arrive together with drought, intense rainfall, or damaging erosion. Changing rainfall can matter as much as changing temperature. A tea garden receiving the same annual total may still suffer if the water arrives through stronger storms followed by longer dry periods. Adaptation, therefore, has to match the place. Shade trees can reduce direct heat and slow moisture loss from the soil. Ground cover and plant residues help protect exposed earth from erosion, while adding organic material as they break down. Improved drainage moves excess water away from roots during heavy rain. Irrigation and stored water can support plants through dry weeks, where local supplies allow it. Growers may alter pruning dates or harvest schedules as seasonal growth shifts. Cultivar selection offers another route. A plant line that performs well in cool, misty hills may struggle in a hotter valley. Other cultivars may tolerate drought, resist a local disease, or maintain useful flavor under stronger sunlight. Weather stations and field sensors can provide precise information about soil moisture, leaf temperature, and approaching storms. Pest monitoring can reveal population increases before severe damage spreads. Each decision depends on rainfall, elevation, soil depth, available labor, and the insects or fungi present in that region. The cup at the end of this journey now carries far more than dried leaves and water. Its bitterness began partly as plant defense. Its earliest human history survives in charred fragments, burial goods, and chemical traces. Tang-era growers and merchants turned tea into an organized system, while Japanese farmers later redesigned the leaf through shading, steaming, and rolling. Global trade carried it through imperial finance and plantation labor. Selective harvesting fixed the chemical starting point, and early heat determined whether the leaf remained green. Rolling controlled its shape. Brewing selected which molecules entered the water, while the tongue and nose converted them into flavor. Human studies then revealed modest physiological effects alongside clear limits of evidence. The same plant now faces changing temperatures, rainfall patterns, and pest pressures that will reshape future harvests. Green tea's remarkable value already exists within this full story. One evergreen leaf connects plant survival with human invention, global history, molecular chemistry, and the uncertain future of agriculture. A cup remains a small daily preparation. Within it rest thousands of years of accumulated technique and the living conditions required to produce the next tender shoot.